You know, electrical circuits can feel like this impossible puzzle. But what if I told you the final exam, the thing that causes so much stress, is actually the treasure map to solving it? We're going to crack open years of these exams to find the handful of core ideas that show up again and again and again. Let's go find those patterns. Okay, so take a look at this crazy web of sources and resistors. It's pulled right from a real exam, and yeah, it's designed to look scary. I mean, this looks like the final boss in a video game, right? But here's the secret. Every final boss has a pattern, a weakness, and the pattern in these exams is exactly what we're here to find. And that is the secret sauce right there. The key to acing electrical circuits isn't about brute force memorization of thousands of different problems. No way. It's about learning to see the simple, fundamental ideas that are just wearing these complex disguises. So let's start pulling off those masks. So where do we start? Well, we start with the core toolkit, the things that let you just slice right through all that complexity. These are the unifying theorems, and you can think of them as your set of master keys for pretty much any circuit diagram you'll ever see. All right, first up, the superposition theorem. The exams love to ask for this one by name. So what is it? It's a really elegant idea for what we call linear circuits, circuits where everything behaves predictably. It just says that if you've got a bunch of power sources, you can figure out the effect of each one by itself and then just add up the results at the end. It turns one massive problem into a few small, easy ones. Which, of course, leads to the million-dollar question, right? When you're staring down that final boss circuit, how in the world do you simplify that tangled mess into something you can actually wrap your head around? How do you boil it down? Okay, get ready for this, because this slide is where it all clicks. On the left, we've got a problem from a 2016 exam. On the right, one from 2021. I mean, really look at these two. The numbers are a tiny bit different, the drawing is slightly changed, but it is the exact same problem. Both of them are testing one single skill. Can you apply Thevenin's theorem? The circuits change, but the real problem, it stays the same. And that brings us to the two heavy hitters, the superstars of simplification, Thevenin's and Norton's theorems. They're basically two sides of the same coin. Thevenin's lets you take any messy part of a circuit and replace it with one simple voltage source and one resistor. Norton's does the exact same thing, but with a current source and a resistor. They are your ultimate weapons for making things simple. And you know what's wild? This essential toolkit, it's actually pretty small. As we scan through these exams, the same names just keep popping up. The maximum power transfer theorem, Kirchhoff's laws, nodal and mesh analysis, and yeah, Laplace transforms for looking at how circuits behave over time. You get a handle on this handful of tools, and you've basically built the foundation to tackle almost anything they can throw at you. Okay, so we've got our DC toolkit sorted. But what happens when the current stops flowing in one direction and starts, well, wiggling back and forth? When we get into alternating current, or AC, it's like learning a whole new language with its own vocabulary and grammar. But as you can probably guess by now, the exams show us it just comes down to a few new keywords. And here it is, the core vocabulary list for AC circuits. Impedance is the big one. Just think of it as resistance, but for AC. Then you've got reactance, which is the specific kind of pushback you get from inductors and capacitors. Resonance is that one magic frequency where those two completely cancel each other out. And finally, power factor, which is basically an efficiency score for your circuit. You master these four terms, and you can decode pretty much any AC problem. And if AC circuits were a movie, this right here would be the poster. It's the classic RLC circuit. And you can really think of these as the three main characters in the story of AC. You've got the resistor, who's always using up energy, the inductor, who stores energy in a magnetic field, and the capacitor, who stores it in an electric field. The entire plot of AC circuits is just the story of how these three interact with each other. Now here's a question that gets to a weird but super important idea in AC. See, power isn't as simple as it is in DC. It's like some of the power is actually doing work, like lighting up a bulb, but some of it is just sort of sloshing back and forth in the circuit, being borrowed and then returned, not really accomplishing anything. So what's the deal with that? And check this out. This table basically answers that question for us. And yep, this is pulled right from an exam question. Active power is the good stuff, the power that does real work, and we measure it in watts. Reactive power is that sloshing energy that's just stored and returned. And apparent power? That's the total of the two combined. It's what the power company has to be ready to supply, even if not all of it's doing useful work. All right, so we've seen the patterns, we've cracked the code of the exams. But that begs the biggest question of all. Why? Why these specific ideas year after year? It's because they're not just for passing a test. They are fundamental to how the real world works. And this isn't just a fluke. We're not guessing here. We pulled these patterns from looking at 8 different final exams. The consistency is just undeniable. These concepts keep showing up because they're the absolute, unshakable bedrock of electrical engineering. There's this one question that pops up that I just love for how simple it sounds. What is transient time? It's not just asking for a textbook definition. It's asking you to think about what happens in that moment of change, that instant when you flip a switch. It's asking about that in-between moment, the physics of how a system gets from one stable point to another. And that right there is the big takeaway from all of this. These things aren't just abstract problems on a test you have to suffer through. Devinen's theorem is used to design our power grids. Resonance is literally how you tune a radio. Power factor decides how efficient our entire world is. These are the fundamental rules that make the device you're holding in your hand right now actually work. So you see, the exam isn't the final boss, it's the treasure map. It shows you exactly what matters. And now you know how to read it.